Salutations! Welcome to the Forest of Bayes. Today we'll be looking at more details of Bayesian analysis. In Bayesian Analysis Module 2, Leaves and Trees, I'm Mark Williamson for DaCCoTA at UND. Let's get our introduction underway, dig our roots into this topic here. Last time we covered the history of basic theory of Bayesian analysis as well as a comparison to frequentist methods. We met our good friend here, Thomas Bayes. Now, let's look at even more details about really getting the computational process down, not just the simple Bayes theorem, but more Bayesian analysis developed from there. We'll look at examples in R, SAS, and SPS for things like Ttest, ANOVA, and regression. So we'll see how this looks like in practice. So again, let's circle back a little bit to the theory. We talked about this already, but a concise summarization is updating probabilities, our degrees of belief, after obtaining new data. That's what Bayes theorems do. We have a certain understanding of, say, the number of birds in our backyard and the number of trees in our backyard. We obtain new data and we update that belief. So here's a couple of different ways of looking at it, whether you want to have sort of words or just new symbols A and B, either way. So what this kind of looks like in practice after sort of continually updating your probability. This is from, I think, archaeological, trying to get in the true understanding of a century for some sort of artifact, something like that. We start out with 0 trials, having really no understanding of century. After 10 trials, it seems like it's around the 15th century, but a lot of uncertainty. But as we get more and more trials, we get more and more certain that it's going to be fairly likely to be close or on the 15th century. So that's kind of a visualization of like what we're doing in Bayesian inference to update our degrees of belief. So let's take a look at some descriptions here, shall we? So there's two ways you can think about doing Bayesian analysis. The first one is hypothesis testing. The other is parameter estimation. Now, there's a real debate on the process, kind of outlined in some of this material here. Hypothesis testing is typically taking a value. So in frequencies, that'd be like a p-value. But in Bayesian, you can use what's called a Bayes factor to test different hypotheses like null, alternative, etc. Whereas estimation with uncertainty gives sort of a point value, like a maximum likelihood or posterior distribution, and then your uncertainty, so confidence intervals with frequentist or highest density intervals with Bayesian. So how this looks like in practice, we say you have data with Z14 hits out of 18. Frequency in Bayesian has single point estimate, so a p-value that's significant for frequentist, and a Bayesian. This is also we don't use significance the same way in Bayes, but this would be a strong evidence against the null. But in the estimation, you give maximum likelihood, or a lot of times mode for Bayesian, and then the interval, so highest density interval or confidence interval. And what this is doing here is, in either case, you're trying to figure out between a null and alternative hypothesis, given no data. And then you feed data, you get your Bayesian posterior, and you see which hypothesis best fits the data. So let's take a little more of that Bayes factor, sometimes known as K. So this is analogous to the p-value or a full versus reduced model comparison. So it is a way of formally comparing competing models in Bayesian analyses. These models might be something simple like the null model and the alternative model, but it might be several models with different parameters. And the nice thing that's different between this and, say, frequencies model comparison is nesting is not necessary. You don't have to. What I mean by nesting is, in like frequencies, it would be like a model has 10 variables, and then it's compared to another model that just took out one of those variables. They're sort of nested versions of each other. Nesting isn't necessary for Bayes factor, so it makes it a little more broadly useful. And so what you do is the ratio of posterior odds for M1, so one of your hypotheses, to prior odds for M1 so that the Bayes factor of much greater than 1 supports M1 over M2. So right here we're looking at the null comparison, and again, this is very small, so it doesn't support the null, it supports the alternative. So that's one thing here we'll see with the Bayes factor. You have to be careful what it's comparing, because if you flip this, if you did the alternative, you flip this around, the number would be bigger. So you have to kind of take some work to interpret it. Make sure you interpret it correctly. And here is typically what different values of Bayes factor tell you. So a lot of times they'll do explanation notation. I kind of did it down to standard notation for better explanation. So if it's less than 1, there's negative support, so it supports the other hypothesis. 1 to 3.6, not really great. After that, you start to have greater and greater support for that hypothesis. And then if it's much greater, it's essentially decisive. So it would be very similar to a very small p-value. Then on the other side of things, again, this highest density interval is analogous to the maximum likelihood with 90% confidence interval. And I think that's all we really need to say there for now. Let's keep working with descriptions. So the items that we'll need for analysis, I have this nice concept illustration here of all that goes in here. We'll start with the prior here. Again, that's that prior information. We have our model. So that along with the data will help build our likelihood. So again, the likelihood is sort of a mathematical description of how that data is distributed. So with all these things, you use Bayes' theorem, get posterior distribution and inference. So some steps for analysis, we'll cover those more in module 3, where we'll see things like defining priors, defining model, and compiling model, etc. We'll also look more at what we can do to sort of the details and tweaking of this posterior distribution. We'll cover that in module 3 as well. But for now here, this is a good enough description to keep us trucking along. So what would specific tests that maybe we can think of in frequentist methods look like for Bayes? So let's start with a t-test here. So you might be looking at a single t-test, like a single value. So you might have this probability distribution, see if it's different from 0. And this one doesn't really look like it is, but maybe say you're looking at 2 groups, you're comparing 2 different probability distributions. The solid lines, those are our posterior, and then I think those are our data. And then like the thin lines, those are our simulated posterior distributions. ANOVA, so this is a great example here. This is going to be like an extended t-test where you have more than 2 groups. This is a great example 9 here on just the level of Machiavellianism in Harry Potter houses. Machiavellianism, you can read that as conniving sort of unpleasantness, and unsurprisingly Slytherin is high up there, but then Ravenclaw and Gryffindor is sort of in the middle, and Hufflepuff looks lower, looking just at the raw sort of summaries. But what you can do is sort of compare every house to each other and you have prior odds and then your posterior odds, and you get something like, say, this is a Bayes factor, and we can see here, unsurprisingly, that it looks like there's a pretty strong difference between Gryffindor and Hufflepuff, Gryffindor and Slytherin, Hufflepuff and everything else, but it doesn't look like Gryffindor or Ravenclaw are any different. And indeed, if we take those intervals, we can see here that hopefully this will show you that Slytherin is significantly higher than other two, Hufflepuff is lower, but Gryffindor and Hufflepuff cannot really be distinguished. So that would be how ANOVA might go. Now regression is going to be a little bit different. This might be one mathy way of translating Bayes' theorem into regression, but this graph or image helps visualize a little more. Instead of the in regression, instead of trying to like figure out if groups are different, you're trying to study things like the true values of slope and intercepts. And I like this here is like, as you have zero data, it could be anything. One data point is sort of a little more constrained. As you add more data points, the distribution of your slope or intercept gets tighter and tighter. And again, here is another way of showing it. You know, a few points, the slope intercept, the fit data could be pretty wide, but as you get more and more, it gets more and more precise. And again, what you can also do these sort of distributions. What you're typically looking for is you might be looking at means and standard deviations as well in Y. Okay, so we will grind our gears a little bit, shift gears to look at some examples. This is going to take a good deal of time because I think running through the examples really helps get our feel for like actually doing Bayesian analysis rather than just sort of talking about it. So we have 3 sets of examples. We'll do R, SAS, and SPSS, and there is more information on sort of the background in these resources here, and they'll be found at the end, links for those. So in R, we'll be using Bayes factor to look at Ttest, ANOVA, and 2 types of regression. We use proc-gen-mod in SAS, use a Ttest, ANOVA again, simple linear regression, and then we'll also look at Poisson regression. So generalized linear models for the win. And then SPSS will keep it a little simpler, Ttest, ANOVA, and simple linear regression. And you can actually get all this R code available that I'll be using here, and then the SAS code here. There is an SPSS code. Just follow along with the pretty pictures of SPSS that I make as we go along. Okay, let's get started on R. We'll look at standard versus Bayesian analysis. I find this is useful to start with something more known. You're probably, hopefully familiar with more standard tests and compared to Bayesian because they should be pretty similar for simple and sort of broad tests. So let's look at Ttest. First, we're going to load in Bayes factor. You'll need to install this first if you haven't already gotten it. We're going to format. We're going to use diff scores. So this is the difference between one set of sleep and another set of sleep. This is like a paired t-test. Start with a t-test of diff scores. And we're looking essentially of, this essentially is also a one sample t-test of is the difference different from 0. So what we find here is test statistics are -4, p-value is significant, which means, yeah, this difference in scores, which is -1.5, was significantly different from 0. Let's look at what this looks like in Bayes. So we're going to use this t-test Bayes factor for diff scores, and we're going to look at both the alternative and null model. So for this alternative model, this is what it gives. It gives alt R. This is really what we want here, and we can see here that this is 17.25. So this is rather large. This is alternative compared to the null. So the larger, the more likely it is that the alternative is the correct. So this gives pretty strong evidence that, yeah, the alternative model, that the mean difference of scores is different from 0 is correct. And if we flip this around, take the inverse, this is the null model compared to the alternative, and we can see that this is actually very small, which means it gives support to the other model, which is the alternative. So both gave us strong support that the difference in scores is not 0. So another thing we can do with Bayes out and beyond the standard frequencies t-test is look at change. So this is change. We'll look more at this in Module 3, but this is ways to simulate the posterior. We're not going to go into too much detail here, but essentially you can run this function posterior on our Bayes factor t-test object we create a summary, but mostly we want to plot these. These traces gives how well it's model diagnostics, but then here's the real meat of it. We give that on highest density interval of our parameters. So mu is that sleep difference. We can see here that it is about -1.5, and we see that the probability of it being 0 is very low indeed, so that's why our alternative hypothesis not equal to 0 was so strongly supported. Now, another thing we can do here in Bayes is do an interval for multiple t-tests. So maybe we want to run another t-test with diff score, but essentially an analog of how you can do like one or two sided t-tests or tailed t-tests. We can set that up where we can change our interval to look at just one side, not negative infinity to 0, so don't look at higher than. And then if we're going to create a new object called all, we're going to have our original one, which had our null and alternative, and then our interval one. So there's 3 different tests, and we can look at the summary of that and also actually plot it. And so what this shows us here is that actually our strongest Bayes factor is here. And then if we show the plot again here, same sort of thing here. And this is now the saying of saying, well, the null wasn't really supported. The alternative was supported pretty strongly, but then alternative, this would be like sort of like a two-tail test. We look at both higher and lower then, but then this is like the one tail where we just concentrate our effort on if it's negative, and since it was negative, it's even stronger evidence, so this is stronger. And you can do this for much more complicated things than just 3 tests, and we'll see that with ANOVA. So with that, yeah, let's see ANOVA here. We're going to format some data here. We're going to use chick weights. So this is a weight of chicks across different feeds. And for standard, we would use ANOVA for this, and then we're going to do a summary, so we can just plot it right here, and we can see that the p-value is highly significant. Then typically you go and do a post hoc test to get which ones are different. We're not going to jump there for this point. Let's just keep going to look at Bayes. Again, it's going to be very similar to the Ttest, only we're using this function ANOVA BF, Bayes factor. Same sort of thing. And we get here that, oh yeah, this is huge. So similar to this is like, yeah, at least one of these is very different, unsurprisingly. So we can continue, again, look at those chains. And now this is showing you that summary. And what this can kind of give you here is, and then this is the plotting the change. And so this gives you sort of the overall mean, like not looking at the different types of feed, and then these are all the different, these are all the different means for the individual feeds. And this is sigma squared, so that's our standard deviation. And then if we go over to the plots here, these are kind of useful to sort of diagnose just which ones are different. And so this takes a little interpretation, because these numbers here, 0 to 60, negative, like these aren't the actual numbers of the chick weight. This is this subtracted from the overall mean. So this is going to be, Casson is going to be, if this 0 here, this is really like 200 and about 260 right here. But we can definitely see there's differences. We can see that horse bean is looks like it's much smaller than all of them. Like it goes from like negative 40. It's sort of its upper end. So that's going to be, so this is going to be higher than that. All these are going to be higher than that. It looks like linseed, though, it might not be significantly different from these. And so you could go through all these and sort of piece it out here. And again, here we can see what I'm trying to show here. So Casson is pretty high. So it's significantly different from horse bean. But if we look at sunflower, the distribution, they're pretty much identical. Casson and sunflower are pretty the same distribution. So not surprisingly, that's what we see here for the distribution. Okay, let's turn around here and do some simple linear regression. So we're going to use this attitude data, format it, and we're going to look at attitude rating versus complaints. So this is like a company's rating versus how well they deal with complaints, not the number of complaints, but how well they deal with them. Here's just a quick plot, and it looks like, yeah, as how someone's score of dealing with complaints goes up, their rating goes up. But is there a significant relationship between the two? So we can use a linear model to run this, get the summary. What we see here is test statistic and p-value that's significant, and this is our estimate here too, which is positive, which means, yeah, it looks like there's a positive relationship as attitude or as complaint resolution goes up, so does. What this looks like in Bayes, we can use the function regression Bayes factor, set our model, run this out, and run change. So with the Bayes factor analysis, our Bayes factor is very large, so supports that there's a relationship. This is our sort of summary of chains. What's useful here is we get means and standard deviation, so means, but really this is the most useful. This is essentially this is going to be our slope, and then the mu is essentially intercept, but this is positive. And another thing that's helpful in the summary, you can get quantiles. So this gives us sort of the numerical version of our graphs. We can see that complaints are going to be 95% of confidence of the slope of the complaints is going to be 0.5 to 0.94. So that's greater than 0. So we can commonly say, yeah, that looks like there is some positive linear relationship. So with multiple linear regression, same sort of thing. Here we're using the same data set of altitude, but instead of just complaints, we're using everything, all the other data, showing the tilde and then just the dot. Here's what comes out, and what we see here is there's 1, 2, 3, 4, 5, 6 different variables. Turns out only complaints, the one we looked at earlier, was significant, though learning was close to being significant. We can do the same sort of thing with Bayes, but now here is, since there's so many variables in here, it actually will compare 63 different models, all the combinations from a single variable all the way up to all of them and any sort of mix and match. So if we look at the length of this object we created, there's actually 63 different things we're looking at. So we don't want to look at all those at once. So we're just going to look at the head of them. If we look at 6, we see here complaints has a very strong setup here, in the thousands. Complaints, this is all compared to the null. And these all are pretty strong, but they're not as strong as this. But what we might want to do here is actually compare the 5 models to the best instead of comparing it to the null, so we can take the head and then by the max and get this second one here. And so complaints, obviously it's its own best fit, so it's 1, but then we can see here the second one has a Bayes factor of about half that, so it doesn't fit as near as well, and it kind of goes down here. And if we plot this, it kind of gives us a nice visualization. Complaints is at 1, and it looks like through here, and then as these get bigger down to the fractional side, they get less explanatory. Looks like while complaints was very useful, we saw that in our frequencies, learning was almost significant, and we can see why. It's found in these top 3 models. Looks like maybe advance, maybe raising privileges, but for the most part, complaints really strongly predicts our rating. Okay, with that, we are done with our first part. You can take assessment 1 here, also found in the links below. Let's pivot into SAS, our next set of step-by-step examples. We'll again look at standard versus Bayesian analysis. So to do a t-test in SAS, we're going to use this SAS help iris, the classic iris data set. We're going to set our data so we can actually manipulate it. Run proc frequency just shows us, okay, we have 3 different plant species, frequency of 50 each. We're going to run means just to kind of show what we have. We're just going to look at, since it's a t-test, just Ttest versus Versicola. Looks like one has Satosa has a mean of 50 and then Versicolor has 59, so we think there's probably a difference. We can again run a histogram to kind of further look at this. It's like, yeah, it looks like there's probably evidence for that. So now let's actually run. So we're going to use this thing GenMod, which can help us with Bayesian analysis. We're going to start with it without Bayes, so we can just do a sort of frequencies and then add in our Bayes to do that. So we have to clarify that we're just looking at the first two, class species, because this is categorical, and then model length, it's a function of species. And this is what we get in proc GenMod here. And how to interpret this is Versicolor is 0, so what that means is it's the intercept, so it has an average of 59, where Satosa is, its estimate is 59 minus 9. So that takes a little bit of interpretation, but that is significant. And unsurprisingly, yeah, 59 is different from about 50. Now, if we add proc generally, add this Bayes, so we got a seed that just is used for reproducibility, and then our coefficient prior, we'll just do a normal. We're not going to get back into setting too complicated of priors. This is what it comes out here, and again, very similar. The intercept, so you can read here, this is Versicolor, it's 59, and then Satosa is 9 less than that. And what we see here, one of the things we have here is our percentiles. You can see here that it's going to be, Satosa is mean is going to be between 9.9 and 8.5, so that is significantly different from 0, which would mean the mean of the same mean as Versicolor. It also, so we get posterior summaries, that's one thing we get. We also get posterior intervals, a little stronger, where essentially this is that highest probability density interval that is sort of equal to the highest density interval that we talked about, kind of different names for it. So again, we see here that it's going to be, the mean of Satosa is going to be between -11 and -7, so that's significantly lower than 0. So we can safely say that, yeah, these are going to be, there's strong evidence that these two are different. Again here. And then intercept is going to be between 58 and 60. So if we, plotted those out, the one would be like, I'm just going to go like 60, 58. So one's going to be here, and then negative those, negative like 7. So well, it's going to be some here. I'm not going to go too much into that. But anyways, another thing we can do here is that comes out. So this is the same thing here. We don't need to write again. I'm just showing them the code that will eventually produce this. I couldn't fit this all on the last page. These are our diagnostic stuff. So intercept, species Satosa, and dispersion. We don't need to really deal with this here, but these are the two. Again, we can see here for, this is Versicolor. Yeah, its mean is around 59, and this is the distribution. And then Satosa here, and again, this middle graph here, because we're subtracting from 59, we could see that here it's going to be something like this true value compared to the Versicolor is going to be like 53, 51, 49, 47. Oops, 47. We'd see that, yeah, 53. The upper end here, is still well below where this would be here. So that the probability distributions put them at different areas that they're significantly different. Okay, so ANOVA will be pretty similar. We're going to use actually the same iris data set, but instead of saying just 2, we'll look at all 3. So look at the sepal length of all 3, and they look pretty different, so I'm not surprised that when we run proc GenMod with just our frequency methods, we find that they all 3 are significantly different from each other. And when we run adding our Bayes in there, when we look at, so again, now because of how these were loaded in, the intercept is going to be Virginica, that its mean is 65, and it goes from 60 64 to 67, whereas Satosa is negative 17 to 13 and 8 to 4. So that all looks significantly different. And again, if we plot this, just sort of put these all on the same scale here. This is a G Virginica again. This is going to be 46, 48, 50, 52, 54, because we're subtracting from the 66. And again, this is going to be 56, 58, 60, 62, 64. So what we can say here is Virginica has the largest sepal length, followed by versicolor, followed by Satosa. Okay, so linear regression. Now here, we're actually going to do a couple steps in the frequentist. I'm going to start with GLMX, Generalized Linear Mixed Model. This is kind of my workhorse, so I understand this the most. I want to be able to do this first so I can understand how GenMod pulls that out as well. So we're going to use this liver data. So it's the number of these liver cancer nodes and a bunch of other variables. So we have time since body mass index, age, time since diagnosis of disease in weeks. This is some biochemical markers. This is it's modeled with 0 and 1. These are anti-hepatitis B antigens, so that's again 0, 1 data. So yes, no. And then presence of jaundice, yes, no. So normal distribution, don't worry too much about that. And then this is going to be very similar, same model in ProcGenMod, it's just using GenMod. So what this looks like in GLMX. First of all, there's some fit statistics. Pearson chi-square degrees of freedom. I'm not going to go into all the details of this, but essentially it should be about 1 or 2. If it's high like this, it suggests not a great fit. So keep that in mind as we move forward. We'll still look at the analysis. It looks like only age was significant. Same sort of thing we'll pull out from GenMod. It'll give the same sort of chi-squared value, and then looks like, again, they're using it slightly different. This is the F value and probability of the F value. This is a walled chi-square. They're a little bit different, but they give the same sort of result. So looks like only age significantly predicted the number of liver nodes. And since this estimate is negative here, we can say that as it looks like what that's telling us, as age goes down slightly, the number of nodes goes up. Okay, so let's look at ProcGenMod. So we're going to add our Bayes in here, not really anything different than we've seen before. Here's our posterior summaries. Mostly we're looking, the useful thing is our means here, because that's essentially going to be our slopes. And then our posterior intervals. And now here, how we interpret this is if they overlap 0, that means the mean, so the slope is not significantly different from 0. So you see here for like BMI, all these things, they overlap. We're not worrying, that's not a variable dispersion, don't worry about it here. The only thing that doesn't overlap is age, which is slightly underneath. So it means that that looks like it's significant. So, though, if we keep moving on here, this is some more output we put. These show our posterior distribution. Again, we can see here that things like BMI, we see the interval is just around 0, and it like encompasses it pretty well. So does time. We can see that 0 is fairly likely under these distributions, so though some are more than others. But then for age, we can see here that looks like 0 is not as likely. It could happen, but it's not as likely, so it's more likely that age is slightly negative. So with that being said, let's turn to maybe a slightly better approach for this data with Poisson regression. We noticed that our fit statistics wasn't that great, so let's do the same sort of thing, but instead of a normal distribution, let's do Poisson. So same sort of thing here, and now actually the chi-squared value is much better. So this is probably better to model liver cancer nodes as a Poisson distributed variable than normal. And indeed, what we see here is a surprising difference. Almost all of the variables other than time are now significant. And the same sort of thing is found for our Procgenmod. Looks like age and BCM, those had negative, so as those go up, nodes go down, but then these ones were positive. As these go up, the liver node number goes up. So again, we can do Procgenmod using Bayes, and again, what we get out here is similar to our frequentist methods, that these ones are significantly different. The slope is significantly different from 0. And as we come here, we see here that, yeah, it looks like BMI, age, time, BCM, AHBA, and jaundice. Of them, only BMI looks like it's not significantly different from 0. Okay, take a little breather here from SAS and turn to the more drag and drop version of SPSS. We will look at standard versus Bayesian. So for a t-test, we're going to be using this this example that they have is ships. Oops, and this is a save file, so you can find this under the example data in SPSS. So if you load the data, you want to look at a chart here. We're going to be looking at ship type, just A and B. There's several types, so we'll just look at type A and B here, and then we're going to look at logarithm of, I think, damage. So to do a graph that just has 2 categories out of multiple categories, you can go over here to custom and have A and B, and then exclude C, D, and E. And so we'll get here aggregate, sorry, not damage, but aggregate months of service, and there might be a difference. B looks like it might be slightly bigger, but let's do a test to find that out. So to run that, we're going to look at Bayesian Statistics under Analyze, and then Independent Samples Normal. And how this will look going out here is we want to set up here our test variable as a logarithm of aggregate months, our grouping variable as that type, and then you can, once you get in there, you're going to need to define groups, come over here and add group 1 and 2. And continue, and then under Bayesian Analysis, you can do posterior distribution or Bayes factor, so one of those 2 methods of analysis, but we want to use both methods. Click OK, and this is what we will get. So group statistics, so ship A had a mean of about 6. This is log months, about 6. This is, or 6.5, this is close to 10. And so then with the Bayes factor, it gives us, so this is our mean, this is Bayes factor very small, and then these are our sort of posterior distribution. So they call this a credible interval. This is going to be equivalent to our HDI, highest density interval. Similar sort of thing here. You can see that the lower bound and upper bound is positive. And so this is a table for the thresholds that SPSS commonly uses. And so if we find our thing here, Bayes factor between these fractions, there's very strong evidence for the alternative hypothesis. So the null hypothesis that these aggregate months of service are the same between the 2 do not look like they're supported. And in fact, we can get some posterior distributions. It looks like the mean difference is around 3. Turning to ANOVA here, we can plot this again using our chart builder, and this time excluding none of them to look at all the ship types A, B, C, D, and E. Looks like these might not be different from each other or even A, but let's do a test to figure that out. We use Bayesian Statistics here, Oneway ANOVA. Again, we'll need to add dependent, that's our logarithm of aggregate months, and then our factors can be ship type. And again, so we want to use both methods. So what we get out here, so it's interesting because it gives both like a F value and significance, so like the standard classical t-test sort of thing. That's why we don't really need to do this frequency method on the side. We can do it. It gives us it at the same time, and then a large Bayes factor. So, and then it gives stuff for each of the ship type. Now this is going to be a troublesome interpretation because we have a huge Bayes factor here, and it says this interpretation says extreme evidence for the null hypothesis. But the null hypothesis, as constructed, should be that there's no difference between groups. However, classical test says there's a significant difference, and we can kind of see with our eyes that, yeah, it looks like ship type B is significantly higher. You know, it's between 8 and 10 than any of the other ones. So it looks like there's a misinterpretation here that whatever this is saying is that there's strong evidence for the alternative. So again, and I haven't been able to find any resources that tells me why why there's a discontinuity between what SAS says it should say and what we can kind of see what it is actually telling us. So that's why like interpretation is really important. So how we can interpret this is, again, there's strong evidence for the alternative, even though it seems the documentation seems to say it would be the opposite of that. But that's clearly against what we visualized and seen and confirmed from other sources. So then we can look here, and with these intervals, we can kind of tease out which ones are significantly different. And really, it looks like this is significantly different from all the other ones, where the other ones really aren't because they overlap each other quite a bit. So there we go, significantly different. All right, with simple linear regression, if we want to plot this, now let's look at the number of aggregate months, but then our X variable is going to be number of damage incidents. So we'll have that on this plot here. We look here, and so what we think here is, yeah, as the number of damage incidents goes up, this probably helps predict how many months of service it's going to be, unsurprisingly. So how we set this up in Bayesian Statistics, go down to linear regression. Our dependent is going to be our logarithm of months, and our covariates is going to be the number of damage incidents. Now at this point, you could also include categorical variables if you added them to the factors, so you can have a mixed, sort of like not so much a mixed model, that's slightly different, but model with both categorical and numerical. We'll just do numerical for now. Use both methods. This is what we get. Now this is called an ANOVA. Just sort of ignore the weird notation. ANOVA and regression can kind of be seen as the same things, doing slightly different things, but don't. I'm getting off into the weeds here. Let's get back to the trees. So again, what this is telling us through the classical test that there's a significant relationship, and then the Bayes factor is large, but again, it's so large, but what the SPSS documentation would suggest that there's extreme evidence for the null, but here, as far as I understand, the null should be that there's no relationship. So again, we have to sort of tread lightly and say that what this is saying is this large number is strong evidence for the alternative rather than the null. And then we can kind of get information about the intercept and slope, and we see here that, so this is the estimate of the mean, so it's not terribly strong, but it's significantly different from 0. So that as, and this is positive, so as the number of damage incidents goes up, so does the number of, well, months it's been active. Okay, with that, we've blown our way through SAS and SPSS, the S starting Ackermans, so we'll use an assessment too to gauge how you did on that. You can find this here, the link here, or the description below. Okay, let's cover some caveats of concern, because we've gone over a lot of stuff and may or may not have waved our hands at a lot of things. So as we've seen from comparing standard to Bayesian analysis in our examples, there's not always a strong difference between frequencies and Bayesian results. While the methodology is different and sort of the interpretation is different, you usually come to the same conclusion on pretty basic examples. Because most of what we cover is relatively trivial, we could almost see with our eyes that it was going to be pretty strong one way or the other. Now, and And what I hoped I kind of showed you with the examples is the usefulness of moving from familiarity to unfamiliarity, starting with things you know, like comparing the t-test, standard t-test to Bayesian t-tests to make sure you understand what's going on. And again, we were starting to get tripped up with the SPSS, seem to have contradictory results. But because we used the familiar test and compared them, we were able to sort of interpret what it should be saying as our conclusions. Some more kind of caveats is our choice of priors, so our prior distribution, can be very important. We really glossed over the fact we just set them as the defaults, or just didn't, let the programs run them under the hood. But we can really set those and work on those later in Module 3. And you also want to really check fit diagnostics when you model your posteriors. Again, we'll look at more of that in Module 3. So this isn't the full story we've seen. Okay, now let's take a look at some more real-world examples. So this is a paper on Bayesian survival analysis in clinical trials. This is a systematic review of trials through PubMed. They looked at 28 articles. And what they found, so there's all sorts of trials and the different Bayesian, so this is specifically based in survival analysis, but different sort of setup they have. Looks like few had external data into priors. So looks like this is being done in clinical trials, but maybe in a more simplistic manner than could be done. Okay, this next one here is on clinical trials, so still the biomedical thing. Looking at different examples to show Bayesian analysis from randomized clinical trials to update about specific treatments in cardiovascular medicine. So they use meta-analysis. So I really like the images they produced here. You can see here they took like observational studies, mass cohort studies, randomized trials to get a final synthesis of odds ratio of all cause mortality at longest follow-up. Same sort of thing here. We're doing the same sort of thing to get a posterior. So that's kind of a nice visualization of this in action. Another review of hematopoietic stem cell mobilization regimes. So this is a systematic review. It was a meta-analysis again, and it had this sort of nice graph here. And really what it's kind of showing is the effectiveness of these different regimes. It looks like the regime that includes long-term SG, GCF plus ME6, the highest mean difference, and like these interactions, I think, also show some of that where they're showing comparisons between regimes. Our last example here is the paper defining FAST2 tree, describing it. This is for phylogenetics, so recomputes all posterior distributions and the log likelihood of trees at each site. So it uses a Bayesian approach. Stuff with trees, but then here's some outcomes where it shows the time to reach a given likelihood. So Bayesian analysis can be pretty time and computationally expensive. We see that FAST2 tree, or adding this other this res XML, they can get pretty good results. Okay, so summary and conclusion here. Again, we'll kind of hammer this point on what Bayesian analysis is. It takes in prior beliefs and evidence to generate posterior beliefs by probability. So the two major methods of using Bayesian analysis, which we've seen, is the Bayes factor for hypothesis testing, so the analog to p-values, and high density interval for estimation with uncertainty, the analog to maximum likelihood. And we saw both of those in action here today. And more importantly, it can be run on a variety of software, including R, SAS, and SPSS, because we just did those. So tune in next time for a much deeper details into Bayesian analysis in our third module, a deep dive. We'll look a lot more into defining priors, looking at diagnostics, etc. Here are the references here, and they'll be available down in the description below as well. As always, DaCCoTA is supported by NIH, so please cite us if you found this information useful, helpful, or otherwise not terrible. Thank you, and see you next time.